Okay, so let's apply this to some really, really cool examples. For example, Newton's law of cooling. When an object is placed in surroundings that are at a lower temperature than the object itself, the temperature of the object decreases proportionally to the difference between the temperature of the object and the temperature of its surroundings. Basically, if I put something hot in a cold environment, the hot thing will eventually get colder. And if I put something cold in a hot environment, it will eventually get hotter. That's the gist of the statement. Now, if I use Newton's law of cooling, he says the following. This is the temperature at any time, T. T naught is the temperature, or the initial temperature at the beginning. Ts is the temperature of the surroundings. Now, over time, the temperature of the object, like I said, will approach the temperature of the surroundings, aka it's a horizontal asymptote. Now, here's an awesome example. The temperature of a recently deceased body is measured and found to be 28 degrees Celsius at 3:30 p.m. and it's 25 degrees Celsius at 4:30 p.m. The air temperature in the room is 20 degrees Celsius. Here are the things that I need to know. Now, check this out. If a body dies, the way that the coroner figures out how long it's been dead is that they take the temperature of the body and they work backwards. That's what we're going to be doing in the next couple of examples. It says here, find an equation to model the temperature of the body where T is the time after the body is found. So the body is found at 3:30. So T, if you need to write this down, T is the time after 3:30 p.m. So let's start with the beginning. T of T is equal to T naught minus Ts, b to the T plus Ts. So we know that initially it was 28. We know that the temperature of the surroundings is 20. B of T plus 20. So I know that it ends up being 25 degrees at the end. So let's finish this up. So you get 25 is equal to 8 b to the T plus 20. Subtract 20. You get 5 is equal to 8 b to the T. Divide by 8. 5 over 8 is b to the T. Well, we know that from 28 degrees Celsius to 25 degrees Celsius, 1 hour has passed. So we know that T is equal to 1. Remember that. So 5 over 8 is equal to b to the 1. So that's what b is. And b, if I put it to a decimal, is 0.625. So my equation is T of T is equal to 8 0.625 to the T plus 20. There's my equation for this body that's decreasing in temperature. If I leave the body in the room indefinitely, what is the temperature that the body reaches? Well, that's again the temperature of the surroundings, which is 20 degrees Celsius. Assuming that I leave the body and that the body temperature is 37 degrees Celsius at the time of death, I want to know when the individual dies. So basically, I know that T of T is 37. I use my equation 0.625 to the T plus 20. I want to now find T, so I want to know when this guy died. So I get 17 is equal to 8, 0.625 to the T divided by 8. I get 17 divided by 8, 0.625 to the T. What I want is in the exponent. I use logs to get out of the exponent. So log 17 over 8 is equal to T log 0.625. So T is log 17 over 8 by log 0.625. If I use my calculator, I get negative 1.60 hours. Well, that doesn't really help me. I need to figure out what time he died, right? I want to know the time of death. Basically, if the coroner comes along to you and says, "Oh, he died 1.6 hours ago," that doesn't tell you anything. So I want to know if I found the body at 3:30, go 1.6 hours back, and zero point 0.6 of an hour is 36 minutes. So basically, if you're using your calculator, you go zero point 0.6 times 60, you get 36 minutes. So this guy died an hour and 36 minutes ago. Basically, that is 1:54 p.m. That's kind of cool, you gotta admit. The last example of the day is basically for anyone who's like me and always burns their tongue when they drink a hot drink. So, though this example is about coffee, it includes tea and hot chocolate, which I am notorious for burning my tongue on. So, it says here the temperature of a cup of coffee in a plastic cup, plastic being the operative word in the sentence, T minutes after it's poured is modeled by the following equation. It says determine the initial temperature of the coffee. If I determine the initial temperature of the coffee, that's at 0 is 61, 0.95 to the 0 plus 18. That's 79 degrees Celsius. How long will it take for the temperature of the coffee to reach 25 degrees Celsius? Well, 25 is equal to 61, 0.95 to the T plus 18. Isolate for T. So you get 7 is equal to 61, 0.95 T. Divide by 61. 7 over 61 is equal to 0.95 T. What I want is in the exponent. How to get an exponent? I take the log of both sides. So basically I get to a point where I say T is equal to log 7 over 61 divided by log 0.95. I use my calculator and I get 42.2 minutes. Now, the second part of the situation says I've got a china cup, so basically a mug, and it's given by this new equation here. It says determine the initial temperature of the cup of coffee if it's in a china cup. Well, that's T at 0, which is 53, 0.98 to the 0 plus 18, which is 71 degrees Celsius. And then it says comment on the rate of heat loss of the china cup compared to the original plastic cup. Well, the plastic cup, the rate was 0.95, it says over here. So it goes down, or it decreases 5% per minute. But the china cup, it says it's 0.8, so that means it decreases at 2% per minute. So which one's better? Well, for someone like me, the plastic cup is better because the temperature drops faster, so that means I can drink my hot chocolate sooner. However, most people like their drinks pretty hot, so they're more likely to drink out of a china cup or a mug. In that case, they want that one instead of the plastic cup. So it really depends on how hot or cold you want your drink to be. It says here determine the time it takes for the temperature within each cup to be equal. So that means 61, 0.95 T plus 18 is equal to 53, 0.98 to the T plus 18. I basically want the two equations to be equal. Well, the 18s don't do anything because they both are the same on each side. So I get to a point where I get 61, 0.95 to the T is equal to 53, 0.98 to the T. Well, I'm not going to do any math right now. I'm going to pull out my calculator, and I'm going to put this into y1 and this into y2, and I'm going to figure out where they intersect. So like I said, I'm going to go to my calculator. I'm going to put the first equation into y1 and the second equation into y2. I'm going to change my window. I'm going to go from 0 to, let's say, 24. I'm going to go up by a scale of 2, and my minimum scale for the y is going to be 0. The highest temperature I'm going to go to is 80. Why? Because I know that the highest temperature for the coffee in the plastic cup is 79, so I want to go at least to 80. And I'm going to go up by 10. So I'm going to graph it, so it's going to look like this. And then I want to find where they intersect. So right here, this is what I'm trying to find. So second, trace, intersect. sorry, second trace, intersect, which is number 5. I want to be before the intersection point, somewhere before it. I'm going to hit enter. First curve, second curve, hit enter. I'm going to let it guess for me, and it's going to come out saying 4.5 and 48.3. So if I was to draw a sketch of this, my sketch would look like this. And that this intersection point was 4.5, 48.4. Therefore, the temperatures will be the same after 4.5 minutes. It says, the last question, in the long term, what temperature will each cup of coffee approach? Well, they'll both approach 18 degrees Celsius. That's it for today. Homework is posted on Blackboard. I hope that this went well, and if you have any questions, please be sure to ask a friend in class, and if need be, go over the note again. Take care.